Welcome. This video is a recorded presentation for the now virtual Symposium on Applied Computing. My name is David Bernbach, and in this talk I will give an overview of our work on using application knowledge to reduce the number of cold starts in FaaS. Serverless FaaS is about running backend code without managing the underlying infrastructure. What we do for that is we write a single function and deploy that with a provider who then handles all the runtime aspects. Examples include OpenWhisk or OpenFaaS, but also commercial offerings like AWS Lambda or Google Cloud Functions. So how does FaaS work in practice? From a cloud provider perspective, we start by having some runtime infrastructure, such as physical or virtual machines. On top of those, we run a number of Docker containers. Each of those containers bundles the executable of a single function. When now a request comes in and arrives at some router component, this component then picks a container that is idle and has already preloaded the function image. Then it sends the request to the function, which executes the request and possibly returns a result. When a request arrives in the system and there's no idle container for that function, a new one needs to be started. This causes a delay. The time in between the request arriving in the system and the start of the execution is also referred to as cold start latency. Of course, cold start latency is something that we'd like to avoid. Cold starts mainly happen when the load increases. This means that we suddenly need more container instances than we already have. Does it really matter? Yes, for two reasons. First, as an application developer, we get the highest benefits out of the FaaS paradigm for really volatile workloads. These, however, cause a lot of cold starts. Second, cold start latency can be up to 1 second, which adds significant delays to the application. So what can we do about it? Well, this is not a completely new topic. Just think of VM startup time optimization. Likewise, there's a lot of research approaches out there that aim to optimize cold start latency. What they all have in common is that they focus on single function cold start latency. What we see, however, in practice is that functions usually invoke other functions, so that we end up with a sequence of functions which gives us additional knowledge. The question is whether we can leverage this knowledge. This brings us to our approach. The basic idea was to use any of the other approaches to optimize cold start latency of all functions, but we also wanted to use this additional knowledge. Namely, when we observed a cold start in the first function, we wanted to notify all other functions which were likely to incur a cold start later on. This way, the cold start would happen out of process, and when our workflow execution arrived in that workflow step, we would have an idle instance available. For this, we developed three approaches: the naive one, the extended one, and the global one. Then we implemented each of them inside a lightweight choreography middleware. In that middleware, there are two different events that can trigger actions. First, when we get a request to execute a workflow. When that happens, we do two things in parallel. First, we start executing the application handler which executes the actual function code. Then we package the result of that function execution into a workflow state object and pass that on to the next function. In parallel, we check whether it was the cold start and whether it was the first function. If both conditions are met, we send out a hint message to all other workflow steps. Of course, we do that asynchronously so as not to block the workflow execution. The second event that can trigger some action is a hint message. In the case of the naive approach, we don't have to do anything at all. Hopefully, the hint message already triggered a cold start in the FaaS platform. While the naive approach works well for very simple workloads that issue a single request every few hours, it has two problems for more complex scenarios. First, the approach assumes identical utilization across all steps of the workflow. This is, however, not very realistic. For example, when we scale up our workload, the first function may be overloaded when the later functions are still completely idle. This means that a number of hint messages will be processed by warm instances and will not cause the desired cold start. Second, we can have workflow overtaking. This can happen whenever the execution of the first function takes longer than the cold start latency of the second function. In that case, we successfully trigger a cold start in the second function via a hint, but when the execution arrives for that step, the cold start is not yet finished and the execution actually triggers another cold start. In the extended approach, we aimed to address the shortcomings of the naive approach and made two modifications. First, we introduced delayed execution. This means that we make the hint message to step 2 a blocking call. This avoids workflow overtaking because the execution just waits for the cold start of the second function to finish. We also introduced recursive hinting. This means that whenever we receive a hint message, we check whether it successfully caused the desired cold start. If not, we send a self-hint to the same function again. In the flowchart of the extended approach, this resulted in 2 changes. In the middle column, we made the hint message to the second step a synchronous call. In the right column, we introduced an action for hint messages. Namely, whenever we get a hint message, we check whether it caused a cold start. If it was not successfully a cold start, we send a self-hint message. This means that the function sends a hint message to itself and then goes into a wait mode for a short period of time. While the extended approach solves some of the problems of the naive approach, it still has 2 problems. First, the approach assumes that the duration of all workflow steps is the same. This is not necessarily realistic. Second, we still have problems with hint misses. What we realized is that both approaches suffer from a lack of global knowledge because they can only ever know about the current state of a single function. For this reason, we developed the global approach. The basic idea is to use monitoring to collect data on the current state of the FaaS system. Then we have a dedicated VM which collects this data, forecasts how the system state will evolve based on queuing theory, and then we send hints at the optimal time. Of course, this also comes with a number of disadvantages. Namely, we have to operate an additional VM which causes costs and complexity. Let's take a look how this works. Inside the middleware, we still have 2 different events that can trigger actions. Whenever we receive a request, we still invoke the application handler, we still add the result to the workflow state, and we still pass that on to the next function. What is new is that we also collect some monitoring data about the function and send this asynchronously to the VM. We no longer send hints inside the middleware. Whenever we get a hint, we just have to wait for a short period of time. This is because the approach may actually send several hint messages at a time, and we don't want to have the same function executing those hint messages. Inside the hint manager running on the dedicated VM, we collect workflow information such as the average arrival rate or the average duration per function. We also collect monitoring state about the current status of each workflow or the current number of busy and idle function instances per function. Inside the hint manager, we can then use this monitoring information to predict future system states. For this, we run a simulation. Based on current known state, we interpolate to the future based on queuing theory. In the second step, we then try to find the best point in time for sending the hints. For this, we identify the point in time where we predict a cold start to happen, subtract from that the predicted cold start latency, and try to find a point in time before that where we have the highest possible utilization for that step function. In the third step, we then schedule all those hints and go back to the first step. This means that we run a simulation round several times per second. How well does it work? Let's take a quick look at our experiment results. For the evaluation of our approaches, we ran a range of different experiments. We used 3 different deployments, one on AWS Lambda only, one on IBM Cloud Functions only, and one federated across both platforms. We used 2 workflow types with different function durations. We also used 2 different workloads. One was a growth workload and one was a burst workload. Finally, we had 3 approaches and 1 baseline experiment, which resulted in a total of 48 setups, which we each repeated 4 times. In terms of results, there are too many to put in this talk. In fact, there were even too many to put in the paper. Nevertheless, this is the key result. The figure on the right shows the percentage of cold starts that could be removed in one of the experiments by our approaches compared to the baseline. So ideally, we would like to have a 100% result for each of our approaches and experiments. That would mean that our approach were able to remove all cold starts. Overall, the global approach managed to achieve a 60 to 80% reduction in cold starts on AWS Lambda. On OpenWhisk, it ran into problems because OpenWhisk uses a queuing feature. This meant that some of the hints actually ended up being queued instead of causing the desired cold start. The extended approach, in contrast, managed to achieve a 40% reduction in cold starts across all experiments and across both platforms. Considering the necessary complexity, the extended approach seems to be a very good choice for all FaaS scenarios. The global approach works best when run only on Lambda. In both cases, costs are actually very low. More details on this are in the paper. To conclude, application clients can actually reduce code starts in FaaS using application knowledge. They don't need any support from the platform provider to do this. Using this approach, improvements of up to 80% can be achieved. Overall, this approach is very inexpensive but adds some complexity which needs to be considered. Thank you for your attention. If you have any questions or comments, please just drop me an email.